Hey guys, let me just share the screen here so we can start. Open the chat. How are you guys today? How's everyone doing? Assuming good. I don't know. I don't receive any response. Great, great. Okay. Yeah, things okay. Finishing up the semester. So are you guys excited about that? Spring is, I don't know if the spring is coming or not, but every day I feel like we're closer to. Okay, so we're going to continue talking about the viscous fluid flow in pipes. I did publish the midterm results just before the lecture. I hope you guys have seen this. The only comment I will have for you here is please make sure that everything is correct. We are not missing anything in the grading. I asked the TA to review it a couple of times. We provided feedbacks for all the questions that you solve. So if you're missing any of these, please send me an email and we can look into that. Okay. I see a correlation between the people attending and the people getting can't open feedback. We cannot see the feedback. Okay. Maybe it is the setting on the Zoom, in the quizzes tool. I will make sure that I can, you guys can access this. So I'll try again to see if the feedback is unlocked or not. Okay, but please make sure that there is no any mistakes in any of the grades. Okay, so I just mentioned, I think I have to say one more thing is there is a correlation between the people attending and the people are kind of, doing okay in the exams. So those who I haven't seen them in the list of the attendee, they tend to kind of struggle a little bit. So I encourage the people who are still attending the lecture, make sure to continue doing so for the rest of the semester. So last time we talked about the fluid flow and piping system, and we basically covered the fracture losses between 2 points on a pipeline. And if you remember, we basically said, okay, if we have a constant diameter pipe that is carrying fluid from point A to point B, we can apply Bernoulli equation between these 2 points. We know the condition at point 1. And if we know the condition at point 2, we can calculate the losses between 1 and 2. And for a straight pipe, we're anticipating some friction between the fluid and itself and the fluid and the pipe. And then we define something called the friction factor. And this friction factor is it's a function of Reynolds number. Okay, if Reynolds number is indicating a laminar case, that means the friction factor is a sole function of the Reynolds number, which is 64 over Reynolds number. If the Reynolds number is indicating turbulent flow, that means the friction factor also depends on the roughness of the pipe, and we introduce something called relative roughness. And we basically used what we call it Moody chart to determine the friction factor. And if you remember, we mentioned also there are many other correlations that can be used, especially when you are using computational codes. We can use this equation in order to calculate the friction factor. But Moody chart is a graphical representation of this friction factor. And we basically solve, I think, a problem on that. The example that we talk about at the end of the lecture last time is, in general, we don't have a very simple problem like this. Most of the time, we have a design problem that is basically indicating that, okay, we have this flow rate, we need to move between point A and point B. We have, maybe a pump that is driving this flow. So the power requirement for this pump is that much, or this is right. So we need to design the pipe. We need to find out the diameter of the pipe, or the opposite. We have the diameter of the pipe, we have the flow rate, and then we need to find out, the power required in order to drive this flow in a pipeline. The only difference between these two is, as you've seen in the first example that we solved last time, it is straightforward because we have the diameter, so we can find out Reynolds number and determine if the flow is laminar or turbulent from the beginning. And it's becoming a straightforward problem that we have to go over step by step. Now let's go and look at, a different kind of problem that where diameter is not given, which means that in this case, we're going to have some kind of challenge to find out these friction factors. So, so let's use this example here, and most of the example for bioflow is just, it shouldn't be a problem. Like, exactly, what you are doing, except for you have to really manage, the information provided and find out the missing friction factor and other part, and then you put the Bernoulli equation to solve the problem. Okay. So in this example here, I have oil, and this oil has a density of 950 kilogram per meter cube. The kinematic viscosity here is 2×10⁻⁵ meters squared per second. The flow rate given here is, 0.342. Let me just add here. This is meter cube per second. Okay. Oh, it's here already. Sorry. Okay. So the pipe was a length of 100 meters. So I know the location. I know the distance between the 2 points in this pipe, or the pipeline length is going to be at 100 meters long, and the roughness of this pipe is 0.06. And if you remember, roughness is related to the material and the finish of this material, or the manufacturing of this material. So it's kind of like, you have a pipe that's going to be 100 meters, and you're going to use this material. Now the total friction losses is given here as 8 meters. He's asking you to find out the pipe diameter. Okay, so what does it mean? It means that I have H loss friction. I know this is basically is F L over D V square over 2G, right? This is given as 8 meters. Okay, so now we have an SI units. So we have to make sure that we are using the correct information and the correct unit for all the information provided here. Okay, so another equation that is exactly the same equation at the top here is like basically F L over D, but now the velocity here can be Q over the area, and the Q here will be Q square over the area square. So the area square is pi over 4 D square. All this will be square because the velocity is a square, so Q square over the area square, and now multiply by 2G. Okay, so this is again equal to 8 meters. Okay, so what do we have for this problem? We have this L is 100 meter. Diameter is not given, right? The Q is given as 0.342. G here is 9.81, right? I can calculate, this equation here. The problem here is we don't have the friction factor. This is actually kinematic viscosity. So this is a kinematic viscosity. So this is density, this is kinematic viscosity. Okay. So now I don't have the friction factor here, and I also don't have the diameter. Okay, so it looks like in order to find out the friction factor, I need to find the Reynolds number, but Reynolds number requires the velocity, but we don't have the, the diameter. So let's just put this equation now. They have an F as a function of the rest here, right? So if you calculate this equation here, basically what you have is, F here will be 8.28, and this is D to the power 5. Okay, so this is equation 1. I know that Reynolds number is rho V D over mu, or V D over nu. Nu is given in this problem, but the Reynolds number here also is not given, right? So I can calculate this, right? So I know Reynolds number here will be the Q over the area. So because this is Q over the area, and the area here is pi over 4d squared. So it looks like, it's going to be d squared and, 1 over d squared times d. So I can also calculate Reynolds number as a function of the damped. So it's 21800 over d. So and this is equation 2. Okay. So it looks like, you cannot find one with respect to the other because the damper is the missing information, which is important information. Now, I don't know if Reynolds number is lower than 2000 or higher than 3000 for laminar or turbulent, right? So I don't know if it's going to be like if I need epsilon over d or not. But again, if we need epsilon over d epsilon is given as 610 to the minus 5, because this is in millimeter. So you have to divide by 1000. So to convert everything in meter, and the diameter here will be given in meter. So this is equation 3. It looks like everything is dependent on the diameter. Okay. In order to solve this type of problem, the easiest way is you have to do some kind of trial and error. Okay. And the trial and error is, it's, you will just assume one value for one of these parameters, find out the information that satisfy all these equations. Okay. The common type solving of this problem is you start with assuming the friction factor. Why? Because the friction factor is within a certain range of most of the fluid mechanics application, right? So I suggest that we use, something like, around 0.01, 0.02, 0.03, something like that. Okay. So it's not going to be like, completely off. What is the difference between assuming a different value is the number of iterative process that you have to do. Okay, so in general you can assume anything, and that's why in the computer codes, if you basically program this equation and then you do some kind of Newton-Raphson algorithm for reiterative scheme, whatever the information you start with, it's just like, the computer will run several iterations until find you the value that is correct, that is basically satisfying all this equation. Okay. So the first thing that we will do is basically for this problem, if we don't know the diameter or we don't know the flow rate, because again, Q is not given, so that means the velocity will be always missing. So in this case, again, we cannot find the information about the friction factor and the rest, right? So we have to assume something. So make it as a standard for your solution is assume friction factor. So if we assume F to be, let's say, I just did it here as 0.03. Okay. So what I have to do in this case, okay, if I assume F is 0.03, so now then equation 1, right? So F is 0.03 equal to 8.28 D to the power 5. So D here can be determined as 0.325 meters. Okay. So once I get the D, I can get Reynolds number here. So Reynolds number from equation 2, Reynolds number here will be 21800 divided by 0.325. This is equal 67,000, right? So it looks like this is we will have different, that's fine. We're still assuming, we didn't say it's going to be 0.03. This is the first iteration, right? So, and then we have to correct it and find out what is the real value, right? What I'm saying here is like, just to not to confuse yourself too much, right? We're going to assume all the time fraction factor, and then we try to correct ourselves. Okay, so the first fraction factor you're going to assume, you are not going to assume 50 or 20, or because those are not numbers that you can see even in the Moody chart. You're going to see something, 0.0012, for example, 0.02 or 0, or 0.2 or something like that, right? So we just assume one number and then we correct it, right? The only difference between one and the other is the first assumption will determine how many iterations you have to do in order to find out the final answer. Okay, so this is turbulent flow. So if you can say that this is going to be a turbulent flow. So this is turbulent flow, right? So in the turbulent flow, we know that epsilon over d and Reynolds number are needed to find out the fraction factor. Epsilon over d, when this is equation 3, right? Equation 3, epsilon over d is becoming 1.85, 10 to the minus 4, and Reynolds number is 67,000, right? In this case, you go to the Moody chart, and in the Moody chart, basically what you're going to do is like you go here. So this is 0.0001, right? And this is 1, 2, 3, 4. So it's 6.7, 10 to the power 4, right? So you go to the Moody chart, if you remember. So 6.7, 10 to the power 4. This is 1 to the power 4. This is 2 to the power 4. This is 2, 3, 4, 5, 6, and this is 7. So there's something in between here, right? And then 0.00185. So it's 0.001 here, and this is like something here, right? So again, there's going to be some approximation for the value that you are getting here, right? And then you can just find out this one here, right? So you get from the Moody chart, shouldn't 6.4 be more than? Yeah, sorry guys, I have double vision, so I'm just trying to see here with the same glass. So if I make any mistake with charts, forgive me, but the idea here is just straightforward. You just need to find out, yeah, I can see it here, 6 point, yeah. Sorry guys, thank you. So this is 6, and this is 8, so this is 7, so it's something here. Okay. So I just like, I think I got it here. So I have the number on my note, and please make sure to check those numbers, right? Okay. So I have F here from Moody charts. I have it on my note here as 0.0203. Okay. What is this telling you here? This is basically the new value. Okay. So the new value here is basically, what you already assume something, and then you try to find out the information based on this value. You end up that the friction factor that you are calculating based on that is 0.023. That means there are some deviation between what you assume and what you are getting out of the equations. Okay. But remember, the equations you will substitute in the equation, and then you go and find out the stuff from Moody chart. So which mean that those number, if your assumption is the perfect assumption, that mean what? That you will get the same exact value, okay? Which is not all the time is the case, right? So what you need to do for this case? Anyone? What do you need to do for this case? Not sure, okay. So when you are putting an assumption and then you, right? So exactly, right? So we're gonna start with a new number that we got and we repeat again, right? So now we're gonna assume F is your new value. Okay. So this is how the iterative method works, right? So in this case, when we put like, you know, a new value like this, so equation 1 will give you a different diameter, right? So diameter here will be 0.301 meter, right? Different number here, right? Reynolds number here will be 72500, right? Epsilon over D is 2 10 to the power minus 4, right? It looks like, again, Moody chart. Okay. So in this case, we'll get the new value here. F new here from the Moody chart is 0.0201. Okay, I actually calculate these values here based on the equation that I have it on my computer, but you know, it's same thing from Moody chart, right? So the Moody chart here is giving you some value here that's close to the value at the back, right? So you assume this value and you are getting this value. This is very close enough, right? So we can say that, for example, this point, 0.0201 is your new friction factor, right? If you use this now, so F is 0.0201. The diameter here is about 0.3 meter, which means the diameter here is 30 centimeter. Okay. We said we're gonna assume a value for friction factor. If you look at this, the Moody chart here, let's say, for example, we don't know how much to assume. It looks like the Moody chart here is what? Something between this and this, right? You see the Moody chart? The friction factor goes from 0.008 on a very, very small value, right? To 0.1 maximum, right? So, and the value 0.001 and 0.01 is very small values here, right? So here, right? So it's something, something here, for example, okay? I'm not saying you have to really assume this, but if you assume even a wrong number, you're just gonna spend a lot of time just like reiterating, okay? So we just assume a value we want. Let me just read the comments here. Yeah, so basically, the assumption will dictate the number of iteration. That's correct, right? So what I'm saying is like, most of the engineering application is something around between 0.02 here, or like even between, something around here to like here, something like that, right? So you are not gonna get that, a value that is completely outside these kind of charts, right? So that's why most of the typical, okay, there is a lot of standards actually in engineering application. For example, velocity in most of the pipeline is between 1 meter, 2 meters per second, something like that, right? It doesn't mean that it's not going to be, 5 meters at some condition or at some system. What I'm saying, most of the typical velocities are 1 to 2, 3 meters per second. Friction factor is between 0.02 and to 0.15 to 0.03, something like that. So try to use some numbers around that. Again, a lot of people asking. after all this, asking how's the initial assumption? I don't know how to answer this. Okay, so the initial assumption is not important. The initial assumption is up to you. Like, if you don't know and you keep asking about like what this number is, I'm just telling you, the number should be something within these charts, right? Because those are the value that you are getting. So, I gave you an advice to use like, 0.02, 0.03, something like that, okay? So you can see in the assumption that I made here, 2 iteration is like done, right? You get the value, right? If you started by 0.001, you might spend like, 3, 4, 5 iterations. Other people use 0.2, for example, they're gonna go on like 5, 7 iterations and stuff like that. Now, how to stop iterations? I guess, it's all depend on the accuracy that you are looking for. So again, if you are talking about like a real engineering problem, you really have to really do the iteration in order to find out those numbers, because small deviation here will affect your, your size of the diameter. So, if you can say I have a like, 5% error, 2% error, something like that, right? For an exams, like, if you are asking me about exams, sometime giving you like to choose like maybe 2 iterations, like tell you, okay, just like stop after the 2nd iteration, okay? Okay, so basically, like, this is the second type of problem where you don't have the diameter, and it's going to be the same as when you are actually if you have the similar problem, and now you don't have, for example, the velocity, like you don't have, you have the diameter, sorry, you have the flow rates, right? But you don't have the diameter. That means you have missing the friction factor. How about if you are given, here, you see here, you have QLH losses, mu, compared to diameter sizing problem. You see here, diameter is given, L is given, H loss friction, right? So it looks like Q is not given, right? And the most important thing about Q is the velocity, okay? So in this case, it will be similar exact problem, but now the velocity is not known, right? So how much velocity that we're going to assume? We're going to assume velocity that is within 1 to 3 meters per second. And then we do the same kind of iteration, same way, right? But in this case, we're going to assume the velocity like 2 meters per second, and then we calculate everything, and then we find out the new velocity and so on, right? So it's going to be like another iteration, that in order to satisfy those equations, right? But the missing information here would be velocity instead of like, the friction factor. Sorry, instead of the diameter. Okay. Okay, so let me just conclude this part of the chapter by some important information for your engineering practice. Okay. I don't mean this to be like, ignored, but this is not part of your exam, right? But I don't care about the exam. This is what you're gonna find out in real life. Like, you will have most of the time, you have, fluid flowing in pipeline, and now you need to design this pipeline, either for your simple engineering project in, as a senior design project, or for your other application. So not all the time is going to be very simple, like sketch like that, right? So you're going to have, there's more additional information you have to know as an engineer about the diameter, okay? This first important information is the nominal diameter, because when you go and buying these diameter, of course, for example, like, the diameter that we got in this problem is 30 centimeter, right? From a material that has this roughness of 0.006, right? Not all the time, you're gonna look for like a cast iron pipe that is a 30 centimeter, right? And you know that, right? You go for a certain standard size of piping from Home Depot, and you will see some standard sizes, right? Same thing for all application of piping. Either this piping is carrying, water like in simple as in the plumbing system, or carrying transportation of waste and wastewater, or carrying oil, for oil transportation, you will see some standard sizes. Those standard sizes go with what we call it a nominal pipe size. Okay, and this nominal pipe size, is referring to the outside diameter for many applications, right? So you will see that the internal diameter here is not, for example, above 14 inches here, or in nominal pipe size 14 and above. The nominal pipe size is the outside diameter. Okay, but in addition to this, thickness is very important. I'm not sure if I don't pass the exam, there won't be any engineering practice to apply. I don't know. Maybe, yeah. I'm trying to, expand the scope of this, because sometimes when you are really designing a system, you really need to find out if this diameter exists, right? So beyond the value that you are getting at the end, right? For any calculation or for any problem, you need to find out if you can really buy these pipe, for example, okay? And also, not all the time it's only pipe diameter, right? Fluid mechanics is covering, covering like, the size of the pipe that you want, but how about the pressure inside, right? So, for example, if you have a high pressure fluid inside the system, right, it's going to be like different thickness of these pipe. Okay, so keep in mind that when you have, this is another chart here for example, for PVC piping, when you have different sizes here, and you can look at, the pipe sizes are commonly found. These are the measurement, the actual measurement that you will see, those diameters. So for example, a 1/2 inch diameter is the diameter actually measurement is 0.84. So which means that, it's going to be some very, difference in the size that you are measuring at an outside diameter. Okay. 8 inches is about 8 inches and 3/4, and these kind of things. Okay. When I talk about the pressure inside the pipe, the pressure inside the pipe is basically dictating how much this pipe can stand fluid pressure inside the system. If you remember from your, I don't know if you've taken design 3 or 2, I don't remember. Have you seen thickness of pressure vessel in any of the courses? In mechanics 2, yeah, mechanics 2, when you are looking at, so the piping is considered to be a pressure vessel, right? So in this case, you can consider like, the thickness here, right? So if you can imagine the pipe will, right? So if you have a pipe like this, and this pipe, it has a pressure inside, right? So it looks like, in order for this pipe to split, right, in order to strain or rupture, right, so there's going to be some pressure build up inside, which is basically like, this pressure is able to break this pipe into halves, and that's why when you start looking into the material that you're going to use for this pipe, the thickness of this pipe, and then you apply, the maximum allowable strength for this material in order to see what kind of thickness based on the pressure inside is equal to. Okay, and that's why you will see, something called the ASME B31.3, and ASME here is the American Society of Mechanical Engineers, which is, the society are responsible for putting the standard for this thickness in the pipeline. And they come up with, a calculation for this design, of these pipes based on some variables inside this pipe. Some of these equations are listed, for example, for ASME B31.3 formula, and this is a modified formula from, Barlow formula here, right? So you will find this Barlow formula is basically listed in many design textbooks. but this, the added to this formula some kind of, a quality factor, like, more of a safety factor in order to make sure that, like, there is nothing break in, in this pipeline in, for example, a power generation facility. Okay, you will see this formula is even becoming different when you are using these pipe, same exact pipe, same exact pressure, same everything. But now you are using a nuclear facility. You will see the thickness of the pipe will be completely different if you are using the application. So again, it depends on the application where you actually you are using. In addition to this, this formula also accounting for how this pipe is made. Is the pipe is seamless, which is those pipe are manufactured by extrusion process, or this pipe is made of sheet and this sheet is welded in order to create this pipe. So all these factors affecting the thickness that you're going to select for these pipe. Okay, so this is additional design or practical value for when you are really selecting a pipeline in a system. So you will add a little bit on the design and mechanics to the fluid mechanics part in order to come up with a final design for this pipeline. So you will see this is just one sheet out of the ASME B31.3. You will see here for different sizes. You see here, this is 1 inch, this is 1.5, 2 inch, and so many for all the pipe sizes. And you will see here, like, a value here, they call it like, the schedule of the pipe. The schedule mean is related to the pressure. So schedule 40, schedule 80, schedule 160, and so on. And for every schedule, that mean we have higher pressure. That mean you will see the thickness here of this piping will be different. Okay. So those are the practical sheets that you will see in your design project, right? So again, this is not something we'll be interested to cover in, as a part of your exercises in this course. But, just to give you an idea about like how can you integrate the information that you get from the, the fluid mechanics, specifically when you are calculating pressure, for example. Okay, you remember the hydraulic gradient line? When we put hydraulic gradient line for piping, if you remember, we said like, if we have a pipe like this, and then we put the hydraulic gradient line, this is the energy line, and this is the hydraulic gradient line. So in this case, this is A, this is B, and this is a datum here, right? Let me just exaggerate here a little bit. So for example, here, okay, you will see like, this is a hydraulic gradient line, and any point on the pipe far from the hydraulic gradient line by the pressure over gamma, right? So you can see the pressure here is like, let's say, for example, this value here, right? Which means that this section of the pipe is going to be made of, different from this section of the pipe. We're talking here about kilometers of piping, right? Let's say. So you see the pressure here value is much smaller than this value, which means that the thickness selected for this pipe here will be, more thicker or more like, higher schedule, because now the pressure inside the pipe is, is higher. Okay. One question for me I'd like to ask here. So where is the highest thickness? Like in terms of like when you have a pump, okay, let's say for example here, this is a pump here that is basically driving the flow. Do you think the pressure here is maximum at the pump, or could be somewhere else? You have a pipeline, you're creating a pumping station, like, this huge pump that is pushing the fluid. There's a pressure at the pump here. So do you see here in this problem, the maximum pressure or the maximum, schedule that you're going to use for this thickness? Is it closer to the pump, or could be somewhere else? Closer to the pump. Okay. Anyone else? What is the maximum pressure inside the system like this? How about, everybody agree with that? right? So it's all like, Jasmine, like, I guess this is basically telling you this, right? So if this distance here is the biggest one, or this distance here, right? So this is basically the pressure over gamma. This is the pressure over gamma. So the pressure here is this distance from the hydraulic gradient line, right? So not in particular, like, the pressure at the pump is the highest point. So all depend on, the tomography of the, of the land, like, how those pipe are kind of, laying around these tomography. So in some points you might see values of the pressure that is even higher than the point that is at the first point of the pump, right? So in order to do this is basically you need to find out the pressure distribution, or like, plot the hydraulic gradient line that we cover in chapter, I guess, 5 for that. Okay. So let me get into the second part of this lecture. The second part of this, any question before I move to the second part? I'm trying to catch up, like, some of the comments here, but forgive me if I can't see some of your, right? Any questions on this so far? Okay. So now the system that we talked about is basically fluid flow and piping system, right? And we said like those piping system, at least consist of like strip pipes, pipe that has the same diameter. So in addition to other, components, and those components are, we call it the fittings, right? And those fittings has many functions, and those function could be, connecting a small pipe to a big pipe. We call it reducer or expansion, or like, installing a valve on this pipeline in order to close, or like, or open, or even to control the flow, or even like to shut down the system when it's like, something happened, right? Different kind of valve that can be installed in this pipeline, in addition to bends, right? So the pipe will not go in a straight line, but it can go, and go around, in the system. So you might see bends that is, 90 degree, 45, and others, right? And again, like, the pressure drop in piping system to determine the flow energy to drive the flow. Okay, at the end, we're gonna find out what kind of size pump that in order to put it on this pipeline in order to drive the flow at these rates. Okay, not all the pipe is, is circular, right? How about if these pipes are non-circular? We have seen many cases when you have ducts, and those ducts are like, for example, the air conditioning ducts or the ventilation system. Okay, why do you think sometimes we need to use, non-circular ducts, for example, rectangular ducts or square ducts? Okay, what do you think sometimes we use this for? Is it an option, choice? What do you think will be the friction losses in circular versus non-circular duct? Non-circular, yes, will consume much more energy, right? So circular will have a smooth kind of, surface. So you have, right? So, but why sometimes we need to use, non-circular ducts? What is the ultimate limitation for that? Anyone think about it? Yeah, to fit a non-circular space. This is exactly what the answer is, right? Most of the time you have this system that is carrying air, for example, in our houses, and, and in order to, utilize the space like HVAC system, that's correct, right? So when you have a system, and this is basically, this is a wall that you have, right? And you need to pass something like this, like, you need to pass air in the corner here, right? So you're going to build a duct like that, right? Okay. Because when you build, imagine this is the space you have available. Let's say it's assumed that this is a space available you have. Let's assume this is the space you have, right? So now you have an option between duct like, rectangle like this, or okay. It's not the best drawing. Okay. So now if you try to utilize the space, because you need to create to maximize the area, right? Because the area inside the circle will be smaller than the area if you have a rectangular space. All right. Imagine if this rectangular space even I think that was not the best. Let me just redraw this so you can imagine and appreciate the difference really. Imagine this is a space, right? Because square and right. While for a circular duct is something like this. Okay. So why in the HVAC system you need to increase the area? Why you want to increase the area here? Let's assume the same airflow rate. Let me just add one more restriction. Same flow rate. You are buying this fan, the blower in the furnace is creating the same flow rate, right? That's the size of the furnace. Why you want to have a bigger area for the same airflow rate? Less velocity. And what is less velocity is creating? I like that. No, yeah, less pressure, less heat, low, yeah, no, more, think more. Okay. It's not properly laminar flows actually has more friction factor. If you see you go the Moody chart, the more laminar flow, the more the friction factor is. So it's not really less vibration, closer, not vibration. Something related to vibration, but it's not vibration. Less noise. Okay. When you have a duct and you have a flow inside these, same as when you open the, when you increase the speed of the fan in your car, right? You hear the noise, right? So which means that the sound of this air flowing in this duct is now creating those noise, right? So most of the time for the HVAC system, you needed a bigger area so the velocity is reduced. That means you are kind of preventing additional noise inside these ducts. Okay. So now in order to treat a non-circular duct, what we're gonna do is the fluid mechanics scientific community come up with some kind of analysis for these non-circular duct, and they end up with something called hydraulic diameter that is equivalent diameter for the circuit. So imagine all the equation that needed a diameter, you're gonna put in this equation, and instead of the diameter of a pipe, right? You're gonna put the hydraulic diameter equivalent to this, right? And this hydraulic diameter for a non-circular duct is considered to be something called 4 times the cross-sectional area. So this area here is cross-sectional area, right? So the cross-sectional area, and then something divided by weighted perimeter. And what is the weighted perimeter? Is the perimeter or the surface or the length is in touch with the fluid, okay? And then you can use same equation, just like, replacing the diameter by the hydraulic diameter, okay? So you can see here, like for example, friction factor is telling you that it is a little bit more than the normal friction factor for the circular diameter. And this is what confirming what you guys said about non-circular duct will have more friction factor, okay? But to find out this hydraulic diameter, you just need to find out the 4 times the cross-sectional area. So imagine you have an area like this. This is A, and this is B. Okay, what is the hydraulic diameter for that? And the fluid is flowing inside this whole duct. The fluid is flowing in the whole duct. What is the hydraulic diameter here? 4 times cross-section area. Can you tell me? AB, yeah. Divided by weighted perimeter. So it's 2A plus 2B. Okay, that's a very simple, right? So how about if you have a water flowing in same pipe? So this is A, this is B, right? And the fluid is flowing here. This is liquid, for example. D hydraulic. 4 times AB, yeah, divided by weighted perimeter. Where is the weighted perimeter? Why 2B and 2C? I don't know what's that. Where is the weighted line between pipe? Is 2C plus B. That's correct, right? So basically, these are the weighted perimeter. This is not weighted perimeter, right? This part here is not a weighted perimeter. It's only the pipe is in touch with here and here and here only, right? So it is basically 2C plus B, right? Excellent, right? Yeah, okay. So let's look at this example here. So you have, you have a tank like this or a reservoir, right? Remember, like, I think I mentioned this many times, but the level of the fluid in a tank is considered to be the energy. Like the level is representing energy. Why? Because every time we have a tank, the point inside the tank has a location, a potential head, plus the pressure head, which is whatever at the top of these points, plus the velocity is square over 2g is 0. That means the level of the tank is considered to be your energy at any point inside the tank, right? We'll talk about this when we talk about hydraulic energy and gradient line, okay? So we have a tank like this. We have a reservoir or a tank. The level H to be maintained at a flow rate of 0.01 meter cube per second. So I have a flow rate here that is coming out, this flow rate here. Don't know what's that. Okay, Q here is 0.01 meter cube per second through a commercial steel annulus. Okay, so this is kind of, if you look at this cross section, right? It's going to be something like this. Right? And the fluid is only moving inside these annulus, right? Okay, so I have this, and this is made of commercial steel, right? So it looks like I just need to find out the epsilon, or the roughness of these commercial steel, from the table of roughness. So to find out epsilon if I want. And this is 30 meters long, so L is 30 meters, right? So this L here is, yeah. The density is given as 1000, so that means it's kind of water, and then the kinematic viscosity. So sorry, so sometime when you convert this, it just doesn't carry the simple, but this is kinematic viscosity, right? For water is that much. Okay, he's asking to find out H. Okay, so what will be H in this case? It looks like if I calculate, you know, between one here, or A and B, right? Between A and B, if I put Bernoulli equation between point A and point B, point A is inside the tank, and point B, you know, just at the exit. Point B pressure is 0 because it's going to outside the atmosphere. There's no mention anything about any other pressure at this point. The pressure inside at point A is basically the pressure head of inside the tank, right? What is going to be you know, missing? Just think about the problem before we start solving. What is going to be missing here is you know, the friction factor to find out H losses. And just happened in this case that the pipe, the flow is moving in an annulus. It's not really, it is a circular annulus, right? But it's not a pipe because it's kind of blocked in the middle, right? So the diameter of this you know, solid part is, you know, this is 3 centimeter, and the diameter here is 5 centimeter, right? Okay. So if you want to, you know, start organized, so you can start by calculating hydraulic diameter, so we can treat everything after that based on what we learned already before, right? So if I look at this, you know, hydraulic, the velocity, I know the velocity, right? I can, let's find the hydraulic diameter first. Hydraulic diameter is 4 times cross-sectional area times the weighted parameter. Okay. So what is the cross-sectional area? 4 times, what is the cross-sectional area? Anyone? I had some active, yeah, so you know, so it's the area between, you know, the two circles, right? So that's correct. So it's pi over 4. You know, the diameter square, the big diameter is 0.05 square minus 0.03 square. So this will be your, you know, the flow area, the cross section of the flow area. And then, okay, y square, why the whole thing is square? I don't know. Anyway, so the weighted parameter here, no, that's okay. Yeah. The weighted parameter here is, that's a tricky part. The weighted parameter here is, weighted parameter here is 2 by, exactly, right? Because it's 2 by r is like, you know, you have 2 lines of weighted parameter here. So the first line here is this one, and the second line here is that much, right? So the weighted perimeter here is 2, perimeter, right? So it is 2 by and R here, which is 0.025, right? Plus this is a big one, and then it's 2 by 0.015. Okay. So you calculate this hydraulic diameter, and I think I did calculate the hydraulic diameter as 0.04. Okay. Now I need to find out minus by 5 minus 3. Sure. Yeah, that's it. Not minus. Why minus? It's not minus. Okay. The perimeter here is added, right? So those are the two lines added. So you are adding the perimeter, you're not subtracting. Okay, so the velocity here is Q over area, right? Q here is given as 0.01 meter cube per second. And the area here is pi over 4, and the diameter is 0.5. So it's 0.05. It's 5 centimeters, right? Divided by area here is 0.03 square, right? So the cross-sectional area, right? I don't know. This is what I have in my calculations here, right? If you guys can calculate, somebody else calculate and check this, but I have 0.04 here, meter as a hydraulic diameter. So velocity here is, you can calculate it from this equation, and this will be 1.99 meter per second, right? So it looks like I have the velocity, I have the diameter, right? So in order to calculate, these heads, right? So what I need to do, so I can assume Bernoulli equation between A and B. A is a point inside the tank, and B is a point just outside of the pipe, okay? So I can say BA over gamma plus ZA plus VA square over 2G equal BB over gamma plus ZB plus VB square over 2G plus H loss from A to B. This is just a straight pipe. There's no fittings, there's nothing, anything. This is basically friction losses. Okay, I just talked the same level of A and B, so they both have the same Z. So these Z and Z are the same, right? Velocity of point A is, okay, okay, so I'm not sure. I don't think, okay, guys, if we forget about the numbers, I think we can, if somebody else can check. So I don't know. I have those numbers here in my notes. So can anyone check those numbers? Okay. So ZA and ZB are the same. So how about the pressure at point B? Zero, right? So this is 0. How about the pressure at point A? rho GH or gamma H, right? So the pressure at point A is gamma times H, which means that this whole equation now become H, right? And the velocity at point A, the velocity at point A zero. Yeah, the assumption here is like straightforward because any point inside the tank, we said the velocity will be zero, right? So this is zero, right? The velocity at point B, VB, is the same as, you know, the 1.99 meter per second. Let me check here my numbers, just make sure that we are, B is, yeah, so the diameter is given here, right? So 5 centimeter and 3 centimeter are diameters. So my calculation should be fine, right? So anyway, anyone got the same number that someone got here? So those are the number I have in my notes, right? Don't think it's going to be a problem if those numbers are wrong. Please check, but I doubt it, you know. So basically you can calculate this velocity here. So this equation now is, yeah, the velocity inside the tank is zero. Yes, because, you know, the tank is like, is considered to be a huge, you know, reservoir, right? So in this case, you know, whatever the flow rate is divided by the area inside of the tank, the area of the tank is big, that means it is basically zero. Okay. So in this case, we have H is equal to, you know, V square over 2G of point B, which is the same velocity, plus losses between A and B, which is F L over D V square over 2G, right? So it looks like I just need to find out the friction factor here. And the friction factor can be calculated based on getting the real number first. So real number here is VD over nu. So V is 1.99. The diameter here is 0.04. This is, remember, this is a hydraulic diameter, right? The nu here is 1.02, 10 to the minus 6. So the value here is 78,000. That means it is turbulent. So in this case, Reynolds number is 7 epsilon over D. If you go and find out, you know, the roughness for a commercialized steel, you will see this value of epsilon is 0.00. It's actually, sorry, 0.046 millimeter, right? So you can say that this is, you know, 10 to the minus 3, and the diameter here is 0.04, right? So the value here is 0.00115. So those two numbers here, you can go to the Moody chart to find out F, which is, I have 0.023 here. Okay. It looks like, you know, this equation here, this equation, right? So I have the value here for F. L is 100 meter. Diameter is again the hydraulic, which is 0.04. The velocity here is 1.99. F here is 0.023, right? The velocity here is 1.99. G is 9.81. So equation 1 will give you H equal 4.1 meters. Okay. Yeah, Yeah, we didn't arrange that much, like, just like we put the equation and now we have h here and the velocity here plus this. So basically, whatever left from the Bernoulli equation is epsilon is, remember, every time we solve the problem, we try to find the material roughness, right? The material roughness is, from last week lectures, is listed in tables. So different material will have different roughness. So commercial steel here is in this table will determine the roughness of this pipe. Okay. Okay. So I don't remember the table name, but please refer to the previous lecture. The only difference in this problem is, basically in this problem is a hydraulic diameter. That's it, right? So can you double check the hydraulic velocity of the lectures? Yeah, okay, sure. Yeah. Sorry, guys. Can you guys check this? So, and if it's wrong, please correct it and just get your values. So the idea here is just focus on the point, okay? So we needed like the elevation of the tank, and in this case, what we need to do is like find out the appropriate hydraulic diameter, okay? So in this case, if we have a non-circular duct, the only difference here is we have to use these equivalent formula here, right? Right. So we are converting a non-circular duct to circular ducts, and then we can find out the rest of the problem is becoming the same. So we treat this as if it's a normal type of pipe, has a diameter. So we calculate Reynolds number the same way, calculate, the same, friction factor based on epsilon over D, but all the diameter here will be hydraulic diameters. Okay. So these are like, yeah, this is, yeah, so I guess I only have 3 minutes here to start the eddy losses. So maybe I will push this into the next lecture so we can cover the eddy losses at that time. Okay, I think I will just stop here, right? I can calculate those numbers again, but I think if somebody else will do this, will be great. I will stop recording here, and then we can carry out with any question you guys have.